Hello everyone, my name is Daniel Liao from the University of Toronto. Today I'm going to be presenting a work that I have performed alongside Professor Sugaya, Amano, and Okawa on the FPGA acceleration of ROS2-based reinforcement learning agents. So here's a brief outline of what we're going to be discussing today. I'm going to start with an introduction to reinforcement learning. I'm going to be laying out some of the challenges in deploying reinforcement learning agents to robots. Then I'm going to be describing our proposed system, which is based on FPGAs. I'm going to be showing you the evaluation that we have performed on this proposed system that used OpenAI GM environments, and we're going to end with a conclusion. So reinforcement learning is a machine learning technique that allows an agent to learn how to perform actions in a way that maximizes the rewards it receives. So here I have a schematic of a standard reinforcement learning problem where an agent reads from an environment a state input, and based on that state, it produces an action output. Based on the action that was produced by the reinforcement learning agent, the environment gives it a reward. So based on this paradigm, the reinforcement learning agent is able to learn how to perform actions in a way that maximizes the rewards. In the field of robotics, these reinforcement learning agents have seen a lot of interest as they can allow robots to solve navigation and control tasks without the need of an explicit model, so in a model-free manner. So many reinforcement learning algorithms exist, and they make use of deep neural networks as nonlinear function approximators to produce the action output given a state input. So here are the two challenges that we have identified on applying reinforcement learning agents to robots. So the first one is a hardware challenge, because since the deep neural networks that are using reinforcement learning algorithms are very demanding in terms of memory and compute resources, and also in terms of power, having a dedicated hardware implementation can be very beneficial. The second challenge is a systems integration challenge, because the hardware module that performs the neural network computation has to be integrated to the broader robot system and has to be able to communicate with the other robot components, such as sensors and actuators. So here are our contributions to these two problems. First, for the hardware front, we describe the design of an FPGA hardware module for reinforcement learning agent inference. Second, for the systems integration part, we describe the integration of this FPGA hardware module to a broader robot system based on ROS2 by making use of the forest tool. So now I'm going to be talking about our proposed hardware design. So in our design, we make use of the technique of quantization. So quantization is a technique that allows the reduction of memory and compute resource usage in deep neural networks at the inference stage. So quantization can be very useful for deploying reinforcement learning networks to robots because of the hardware constraints that robotics embedded systems have. So in our research, we studied three different quantization schemes. The first one we call FP16 quantization. So FP16 essentially converts the 32-bit weights and biases that were obtained during the training stage to 16-bit values. In here, activations, which are the inputs and outputs of each neural network layer, are not quantized. The second scheme is called FP16 full quantization. It is very similar to FP16, but it also quantizes activations. The third scheme is called int8 uniform affine quantization. So here, activations are not quantized, and weights and biases are quantized to 8 bits, according to the following formula. So this formula divides the values in the weight matrix into 2 to the n equally spaced values. This allows the weights and the biases to be stored as 8-bit values. However, to perform computations, they need to be converted back to floating point by multiplying the quantized weights by the quantization factor. Now we describe the structure of our FPGA neural network module. So the FPGA neural network module was designed using Vivado HLS. This design only applies to the inference stage. we performed training previously on a PC and we exported the weights to the FPGA. So the weights and the biases, which were exported from the PC, were quantized and are stored in read-only memories. These memories are partitioned to allow for concurrent execution of multiply accumulate operations. Inputs and outputs arrive and leave the FPGA via the XC stream protocol. The structure of our design is such that the output of one module is the input of the next. This allows us to use the HLS data flow pragma. This pragma enables task-level parallelism, so it enables different submodules to start execution concurrently, and this enhances the parallelism of the design. Now I'm going to be describing how we integrate this FPGA hardware module to a broader robot system. So we integrate the module to a ROS2 system. ROS2 is a framework for robot development that has widespread usage in the field of robotics. So we automatically and seamlessly integrate the FPGA hardware module to ROS2 by making use of an open source tool called Forest that we have developed. So given an FPGA HLS design in a configuration file, Forest is able to generate a ROS2 interface for the FPGA module. It maps the HLS input and output data types to ROS2 data types. So in the example here, I have a neural network from HLS that has a state input, which is an array of 4 floating point values, and an action output, which is an array of 2 floating point values. The state input gets converted to the corresponding ROS2 data type, which is float 32, and same for the action output. So Forest is able to perform this conversion for multiple different and general data types. So Forest builds this structure that we call a ROS2 FPGA node. So it essentially wraps the FPGA logic into a ROS2 node. It creates a ROS2 interface, which is a fully software interface, and a PINC driver. So by having this structure, any external nodes can communicate with the FPGA, meaning sending inputs to the FPGA and receiving outputs from the FPGA very easily. This is because for the external nodes, the FPGA behaves just as any ROS2 node would. In order to send inputs to the FPGA, external nodes simply need to publish to the FPGA in topic. And to receive outputs from computations, they simply need to subscribe to the FPGA out topic. The ROS2 node interface and the PINC driver are automatically generated by Forest given the FPGA HLS design. Here is a schematic of the integration flow that we follow to integrate the FPGA hardware module to a ROS2 system. So first, based on the FPGA HLS module that we have described previously and on a configuration file, Forest generates the ROS2 FPGA node structure and an input and output ROS2 topic for the ROS2 FPGA node. After this structure is generated, it is really easy to integrate the FPGA to the robot system. Here, a sensor running on a ROS2 node can publish state inputs to the FPGA in topic, and the actuators of the robot can subscribe to the FPGA out topic to get action outputs. Now I'm going to be talking about the evaluation that we have performed on this proposed system that made use of OpenAI Gym environments. So OpenAI Gym is a framework that contains widely used simulation benchmarks for reinforcement learning. Our proposed system was evaluated in 3 such benchmarks. The first one is Carpole V1, which consists of a cart on a frictionless track whose goal is to balance a pole and prevent it from falling over. The second one is Acrobat V1, which consists of 2 joints and 2 links, which are initially hanging downwards, and the goal of the environment is to swing the lower link up to a predetermined height. The third benchmark is Pendulum V0, which consists of the classic inverted pendulum swing up problem. So the pendulum starts in a randomized position and must be swung up so that it stays upright. Here's a schematic of our evaluation setup. So for our evaluation, the FPGA board that we used is a low-cost Digilant Zibo Z720 SoC. The FPGA logic performance was compared to software logic running on a modern Intel CPU. So here's our evaluation setup. We have an OpenAI Gym simulation running on a ROS2 node which runs on a PC. The simulation environment publishes state inputs to the FPGA in topic. The ROS2 FPGA node receives the state inputs, and the generated ping interface sends the state inputs to the FPGA hardware, where action outputs are computed. The action outputs are then sent back to the simulation node, which runs on the PC, and the simulation proceeds this way. Communication between the PC and the FPGA SoC is achieved through Ethernet, which is supported by ROS2. Here are the evaluation results in terms of latency. We made use of the three quantization schemes that we described previously, FP16, FP16 full, and int8. We also compared with an FPGA design, which we call here FPGA float, which uses no quantization. And we also have here the Intel CPU. In all three environments, we observed that the FPGA design was able to perform the neural network computation faster than the Intel CPU, with a mean speed up in the range between 3.36 times and 3.4 times. So even though some of the quantization schemes use less bits than the others, we saw very little latency improvement by doing quantization. This is because even though some of them use less bits than the others, they all make use of floating point computations. Further latency reductions could be achieved by making use of fixed point computations at the expense of accuracy. Here are the evaluation results in terms of accuracy. To test the impact of quantization on accuracy, we recorded the rewards that each of the modules received across all three environments. It was observed that both the non-quantized scheme and the FP16 quantization scheme had average rewards superior to the CPU. Thus, the FP16 scheme did not have a significant negative impact on accuracy. An accuracy penalty was observed for the FP16 full and for the int8 quantization schemes. In terms of power, the power consumed by the FPGA board was around 2 watts, which makes it suitable for embedding into robots. Furthermore, a power consumption reduction of over 10 times was observed when comparing the FPGA designs to the Intel CPU. To evaluate hardware resource usage, we compared each of the quantized designs to the non-quantized FPGA design. The largest reduction in hardware resource usage was observed for the FP16 full quantization. This was expected because the FP16 full quantization scheme, besides quantizing the weight matrices, also quantizes activations. So to conclude, in our work, we have proposed an FPGA-based reinforcement learning neural network for inference, as well as a methodology for integrating this FPGA hardware module to a robot system based on ROS2. The proposed system was evaluated in 3 reinforcement learning simulation environments from OpenAI Gym, and the proposed FPGA system was observed to provide up to a 3.69 times speed up and up to 52.7 times better performance per watt when compared to an agent running on a modern Intel CPU. So with that, I'd like to conclude my presentation. Thank you very much for watching.